So this is kind of the gauntlet topic that many have heard about. And we alluded to this topic when we talked about improper integration. So improper integration, we were finding the area of an unbounded region, and we mentioned that that was very similar to an infinite series, because when you're finding area, you can think of area as a collection of rectangles that you're adding up. Again, sorry for the watermark on the bottom of the test. We had a plant that overflowed onto the counter. The infinite series that's sort of behind the scenes is what we're going to look at now. So improper integration is kind of a hint at that idea, a hint that you can add up an infinite number of positive numbers and get a finite answer. That's what improper integration told us, that an infinite collection of positive numbers can actually have a finite sum. So we're going to back up a tiny bit. What sits below infinite series are infinite sequences. And the way we are going to analyze infinite series is through an infinite sequence. So we're going to talk about the basics of sequences and series in 10.1, and then we'll get into the details of sequences in 10.2, and then details of series in the subsequent section. So first off, in math, when we say sequence, it's understood that it's going to be an infinite sequence, not a finite sequence. If we are dealing with a finite sequence, they're going to tell us. So we're going to assume that a sequence is infinite, and same thing with the series. We just sort of assume when someone mentions the word series in math that we have an infinite addition, an infinite sum, unless otherwise noted. So for a sequence, there are two ways to describe these infinite sequences. We can generate them with either an explicit formula, or we can generate this infinite sequence with something called a recurrence relation. In calculus, 95% of the time we're dealing with explicit formulas. So we're going to have a formula that says, this is how we're going to generate the terms in this sequence. So this formula is a function, and that function is telling us how we're going to find each of the individual entries in the sequence. A recurrence relation, you build a subsequent term by doing something to the prior term. So that's very different than, oh, sorry about that, yeah. Sticking out. Oh, sorry. With an explicit formula, you're basing that function on the index. And so the index acts like an x value that you're plugging into a function, and you generate your term value. With a recurrence relation, you look at the prior term and do something to that to create the subsequent term. And you all know one really famous infinite sequence that is a recurrence relation. Anyone have an infinite recurrence relation sequence that they can, what one?
Counting?
Counting is actually, yeah. What do you do to the prior term? You add one. Yeah, that's great, that's true. But there's a really famous one. Fibonacci sequence, you add the prior two terms to get to the next one, so it goes 1, and then you add those to get 2, and then you add the 2 and the 1 to get 3, and then the 3 and the 2 to get 5, and then the 5 and the 3, blah, blah, blah. So that's a famous recurrence relation. We're going to be dealing mostly with explicit formulas, but we'll deal with a couple of recurrence ones. So the notation for a sequence, there's lots of notations. You know, this sort of general listing of the terms, the dots just mean it goes forever, or you could do it like this. Most of the time we just write a sequence like that. That means that it's an infinite sequence. It means that most likely you start at n equals 1, but sometimes sequences can start at 0. Sometimes it can start at, another positive number. Who knows? It depends on what's happening. There's all sorts of reasons why it might start at 0 or 1 or some other number. It does not matter at this point. All you have to care about is that there's a list of numbers. Wherever you start, you just keep adding 1 to the index to keep on going. And you need some method of creating the value of the terms. Okay, so when we are thinking of sequences, the most important sequence that you are going to encounter is called the harmonic sequence. It is the sequence of reciprocals. So it's going to start at 1 and go on forever. And so the first term of the sequence is 1. And we typically want to think of our sequences as functions. And so you can picture them as graphs. You can picture the graphs as if the n values or the indices are the x-coordinates. So a sequence would be a discontinuous function because there's gaps. Right? We're not just drawing like a parabola or an ellipse or something. The function's graph is just this collection of dots. So we think of a sequence as a discrete object, not a continuous object. So there's gaps between the sequence values. So clearly not a continuous function, but you can see that this sequence is a subset of that continuous function f of x equals 1 over x. Right? The dots are a subset of this continuous function. So that's going to be important to us when we start talking about whether a sequence converges or not. And you can kind of see that, oh, this function has a limit of 0, 1 over x as x goes to infinity. And that's going to tell us that, 1 over n as n goes to infinity will have the same limit of 0. So if you have a sequence that's embedded within a function that converges, then the sequence has to converge also. So we'll talk about that. Limit of a sequence, same as the limit of a function. You're just looking for a number that the sequence approaches as you go far out into the tail. So conceptually, we say that a sequence converges to L if the terms in the sequence become arbitrarily close to that number L. They get infinitely close. So the sequence of terms so they approach a single number that we call L if they get infinitely close to that single number L. So L in this case is 0. They're approaching the x-axis, which is y equals 0. If the sequence does not approach a single number, just like if a function doesn't approach a single number, we say the limit does not exist. And there are several ways that a limit cannot exist. The function can go to infinity. And that's one way. It can diverge like that. It could oscillate. Those are two common ways. There's other ways that it might not exist, but those are the two common ways. When we think about a sequence or a function that has a limit that doesn't exist, we generally think of going off to infinity, maybe an asymptote, or some sort of oscillation like sine of x, something like that. In this case, our harmonic sequence converges to 0. The terms are getting arbitrarily close to 0. Well, we can take that harmonic sequence and we can throw in a little twist here. We can put in something called a switch, and we can make it an alternating harmonic sequence by making every other term negative. So the first term is 1, the second term is negative 1/2, the third term is positive 1/3, the negative 1/4, etc. So that's the alternating harmonic sequence. And you can see from the graph that it also converges to 0. And if you think about some of the things we've talked about with limits of functions, the numerator here is bounded. The numerator is either negative 1 or positive 1, but the denominator is increasing towards infinity, so that's going to force the fraction values to go to 0. Right? If the numerator is bounded, if it's trapped between, in this case, between negative 1 and 1, if the denominator keeps getting bigger, the fractions have to get smaller. And we can see it from the graph also. So the limit is 0. And we often call this term the switch. And who knows whether it's the odd indexed terms or the even indexed terms that are negative. It all depends on whether you have an n or an n plus 1 as the exponent on that negative 1 on the switch. It's called the switch because it's switching signs. Okay, so here are a few sequences. And again, when we use the word sequence, we mean infinite sequence. We're not going to always call everything an infinite sequence. We just say sequence and it means infinite. Finite sequences are much more unique. They take, and then they'll tell us if they want us to deal with a finite sequence. So these are all infinite sequences. So the first one says, or the first part for all three of these, say find the next two terms in the sequence. So we're just looking for the pattern here. And what would the next term in the sequence be?
14.
14. So the next term is 14. This is a recursive sequence because we are getting to the subsequent term from the prior term. So this is recursive, not a function. And then the term after that, 17, etc. So those are the terms that are in the middle there after the 11. And you can see it pretty clearly that it's a recursive sequence. So it now says, let's find. And actually, I'm going to be a little more careful here and write all these terms out because we are going to need to analyze the index when we find the explicit formula. So let me just put them all in here just so that we can look. So when we think about the indices, this, we're told it starts at 1. So I will often put the indices down below in a different color so that we can kind of think about how to get the term value from its corresponding index value. So there's our sequence. That's part A. Just list the terms. Find a recurrence relation. So there are two pieces to a recurrence relation. We need to say how we get to the next term from the prior term. So the next term is n plus 1. N is the prior term. And what are we doing to the prior term?
Adding 3.
Adding 3. But we also need to know where we're starting. And so we have to indicate what the first term in the sequence is. So that is how we would define a recurrence relation. We have a starting point, and we have a way to get to the next term. So if a sub 1 is 2, we plug in the 2 there, we get the next term, which is 5. Then we plug in the 5 there, we add 3, we get the next term, which is 8. So that's how a recurrence relation works. We take one term and we build the next term from it. So that's part B. Part C, explicit formula. So again, this is the piece that is more, this is most of the sequences that we deal with, we're going to have an explicit formula that tells us how to build the terms from the index. So when we look at this, we have to start looking for a pattern here. Can anyone, any ideas of how we could build a formula? So we want to get to the 11 from the 4. We want to get to the 5 from the 14. So we want to use that index to sort of build a function that satisfies that. Can we see it?
Times 3 minus 1.
So say that once again.
Times 3 minus 1.
So let's see. So times by 3 and then subtract 1.
Yeah.
So if we plug in the 1, multiply by 3, we get 3, subtract 1, we get 2. Take this, multiply by 3, subtract 1, we get multiply them. Yeah, so yes, that works.
Okay.
Now, this is hard to do. It's not obvious, especially to everyone. Everyone's going to see something differently. What I find if I'm trying to figure out the recurrence relation, what I typically will do is write down a bunch of things. So like if we think about the terms, like if I was doing this at home, dealing with a complicated sequence, trying to find the recurrence relation, you can use a spreadsheet. You can put your terms in one column. You could, so this is your a sub n. You can put your n in another column, 1, 2, 3, 4, etc. You can then start doing things to the n. So you could do like n squared is sometimes an option. Maybe that's going to be helpful. 2n is sometimes helpful. So you just start trying things until you see a pattern. So I'm not multiplying by 2 very well here. So 2, 4, 6, 8. Multiply by 3. So you're just going to do things until you see a pattern. And when we look at this column and we look at our a sub n, we start saying, oh, look, they're connected. They're all one off. So yeah, if we take n, multiply it by 3, and subtract 1, we get to our a sub n. So it's not always easy to find a pattern. It's not going to jump out at you. But if you do some sort of systematic, spreadsheet-y type thing, a lot of times that's helpful. And no one's going to give us a sequence in this book that's super complicated. So if we look at some basic ways to manipulate n, square it, maybe cube it, multiply it by 2 or 3, it's usually a decent way to get at it. Okay, so let's look at this one. This one again feels very recursive. We're simply dividing the prior term by 2. So if we continue in this pattern, this is how the sequence is going to continue to go. They just asked for 2 terms, but we're going to just keep going just for the heck of it. So the terms you can see are never going to go negative, right? Because we just keep dividing by positive 2. So those are the subsequent terms. And pretty obvious that we get to our subsequent term by taking our prior term and dividing by 2. So there's our recursive step there. That says the next term is the prior term divided by 2. But then we need to know where to start. If someone just says, hey, build a sequence where the next term is the prior divided by 2, you need to know where to start. So that's where we have to also include that our first term is going to be 64. So that's the first number we plug into the a sub n. And then we get the next term by dividing that by 2, and etc. Okay, let's see if we can build our our function representation. So we have that. One thing we notice, if we come over here, let's do this little table idea. So if we look at our n values, maybe hopefully 4 or 5 is enough. A sub n, 64, 32, 16, 8, 4. So one of the things I notice is that we have powers of 2. Maybe actually what I'll do is even explicitly state that in this step. And this is 2 to the 2, this is 2 to the 3, this is 2 to the 4, this is 2 to the 5, this is 2 to the 6. And anybody see anything that might help us here? Any ideas for another column or for a possible formula? What do you notice about the n and the exponent? What's true? What's a pattern there? Say once again. So they all add up to 7, and then this is 1 less than that, right? So these add up to 7, those add up to 7, those add up to 7. This one is 1 less than 7. This one is 2 less than 7. This one is 3 less than 7. This one is 4 less than 7. That one's 5 less than 7. So what we could do is build it like that. We could say that a sub n is 2 to the 7 minus n. All right, so that first one is 1 less than 7, 2 to the 6. The second one is 2 less than 7. So we can see that that's a pattern there that we could exploit, and we could get a formula. Now you could write this in a couple of different ways too. You could write this as 2 to the 7 over 2 to the n, right, using laws of exponents. You could do that. 2 to the negative n is 1 over 2 to the n. So you could separate this. If you know your laws of exponents, which you should by now. All right, let's do one more of these crafty buggers. Actually, why don't you all start that crafty bugger while I hand out the rest of the folks that came in. So, Chewy, Trayvon, Alvaro.
I like immediately to associate those.
Perfect square. Perfect square.
Sorry about the watermarks. The water plant had
What's the number of that?
leaks.
49.
Yeah. 64.
All right, you keep working on that.
I can
grab
just-
it.
I remember doing this in IB.
Yeah, we did it with the SAT and stuff. But like they didn't call it.
It just means it's only gonna get harder. How'd you guys? How'd you get it?
Okay, so this one is going to be a little bit easier to find the explicit formula for. Next term is
36, 49.
36, 49, so we're dealing with squares. And if we put our index down below, we see pretty clearly that we just take the index and square it. So part C is going to be easy here. Part C is going to be that a sub n is nothing more than n squared. So part C is the easy one in this case. And the prior to part B was the easier one. So here, we're going to start with 1, and then the next term, a sub n plus 1, is going to be something with the prior term. So we've got to somehow figure out what to do to a sub n to get this net, whatever it is. It's like if we focus here, we need to be able to get to this 16 from this 9. And we have to, so we're going to get to this 16 by using that 4 down there. So somehow we've got to sort of indirectly or maybe directly get to the index values. Because one thing we know that, okay, well this is 4 squared and the prior term is 3 squared. So if I want to get to the 16 from the 9, you could do this kind of path. You could say, oh, well, I can get to the index for the 9 by taking the square root. And then we can get to the index for the 16 by adding 1. And then we can get up to the 16 by then squaring that index value. So if we have our term, we could take its square root to get down to its index value, then add 1 to get to the subsequent term, and then square that. So that is going to be the key. We're going to take the square root of the prior term. That gives us the index value of the prior term. And then we add 1 to get to the index value of the current term, but then we square it. And that will give us our next term. So if we start from the beginning, when we plug in a 1, square root of 1 is 1, 1 plus 1 is 2, 2 squared is 4. Then we plug in a 4, square root of 4 is 2, 2 plus 1 is 3, 3 squared is 9, etc. So that'll be our formula for that. Any questions on this idea of sequences and how you generate the terms recursively or explicitly? All right, so we have a, Jose, did I give you yours? Did I give you yours? So let's talk about the test for a minute now that we have more people here. So the average was a little lower than the last test. The high was a little higher, but the distribution we still had, kind of a similar distribution. There's a couple of things that you've got to be aware of. One is that the next test is harder than the prior two. That's the hardest test of the semester, is the infinite series test. So that means whatever you did on the last test, especially if you were sort of below a B, you definitely want to change your study habits because you need to do more than what you did before in order to do well on exam 3. If you have done badly on both exams so far, obviously the final replaces the low one, but if you've done bad on 2 exams, then one of those has to count. And there's a lot of things to think about when you're going down the path of doing a science major. If you're going to go into engineering, which a lot of you are planning on, there's 3 very hard classes as an undergraduate. There's Calc 2, there's Calc 3, and there's Physics 2. Those tend to be the 3 hardest classes. Now, in terms of the math sequence, Calc 2 and Calc 3 are very hard, and then you get to differential equations and linear algebra where it eases up. Those classes tend for almost all students to be easier on the brain than Calc 2 and Calc 3. And when you're going in, if you're going into engineering, that's a nice thing that the math starts to get easier after Calc 3. There are many folks that successfully complete engineering degrees and have to retake either Calc 2, Calc 3, or Physics 2, or maybe even a couple of them. So doing bad your first time in Calc 2 or Calc 3 or Physics 2 is not, it's not a death sentence. There's plenty of people that have to do a retake on one of those courses. Because the bottom line is that when you get into the higher level courses, you have to be good at calculus. Those courses are easier if you know your calculus. But if you aren't solid in your calculus, then it's just going to get worse. So you want to make sure that you have a solid base before you go on. And what I've noticed on the test, for those of you that are in the other category, is that for most of you, it's the prerequisite stuff. It's the trig, it's the pre-calculus, it's the Calc 1 derivative things. You know, like if you are making some of these really, sort of algebraic mistakes, doing this kind of thing, splitting this into square root of x plus square root of y. One of the other mistakes I saw was splitting a fraction in the wrong direction. Like these mistakes, you cannot be making at this level. These are Algebra 1 mistakes, Algebra 2 perhaps. And you cannot be making these in Calculus 2. And if your inclination when you're doing your math is to do some of these things, you've got to sort of beat that out of yourself, because that's just a big problem. Because a lot of these things, and even reverse chain rule, if you are not doing reverse chain rule correctly by now, so like in the integration by parts thing, we saw a lot, I saw several of this type of thing. So let's suppose we had that as our integration by parts, so we have to integrate this. So this should be negative cosine 2x divided by 2, but I saw that a bunch. Like these sort of basic mistakes, you can't be making them at this level. When you get into Calc 3, DiffEq, if you're making those kind of mistakes, you're just doomed. I mean, to be honest, you're just doomed. It's way better to retake a class before you get beyond. Like you don't want to be in Calc 3 scraping through Calc 2 with a C. I've taught these courses for 30 years, and I've taught Calc 3 40 times. You do not see calculus grades do this. This is not the curve of calculus grades. When I look at Calc 1, Calc 2, Calc 3 grades, that's not what they do. They do this. They stay the same or go down, right? Because there's so much prereq stuff that's built. Math is the only sequence in all of undergraduate that has so much that's built on the prior course. It's very recursive. It builds on the prior stuff. Like you just don't see this in other prefixes. In physics, you have it a little bit. Chemistry, a little bit. But we have college algebra, pre-calculus, Calc 1, Calc 2, Calc 3, and they all just build dramatically on each other. So any gaps that you have, you've got to figure out how to fill those in, and it's absolutely possible, but it is going to mean that if you're making algebra type mistakes, it means you've got to do something if you are honestly sincere about wanting to get an engineering degree, you've got to take that serious. Those holes that you have in your boat, you've got to fill those leaks in. Calc 2 is the first class where they really can reveal themselves. Calc 1, you use some algebra, you use some trig, but not like Calc 2 and Calc 3. We use trig and algebra every day. And we don't use the basic trig and the basic algebra. We're using complicated trig. You need to know your unit circle inside and out. If you don't know your unit circle inside and out, it just sucks. Because you're sitting there trying to remember what, the inverse sine range is when you shouldn't be thinking about that. Finding the range of the inverse sine or the inverse tangent or the inverse cosine, at this stage in your math experience, that should be like factoring polynomials. Like that should be really easy. And if it's not, you need to make it easy by just doing some more background work. And I even saw factoring problems, which this factoring on the exam, we had an x to the fourth plus 5x squared plus 4. If this takes you more than 10 seconds to factor, you are not good at factoring. And you need to do something because factoring is just everywhere as you go through Calc 2 and Calc 3. When this coefficient is 1, and this is like a small number that only has 2 options, it's either 2 times 2 or 4 times 1, if this takes you more than 10 seconds, that's a problem, and you've got to fix it. Because going forward, Calc 3, DiffEq, physics, no one is going to think that you can't factor that in less than 10 seconds. So when you get into other classes, it's very likely that this could be a non-prime number out here. You could have a 4 where there's a bazillion options, or 6 or 9. When that's a 1, there's no choice, right? You're right in this position automatically. That's where you start. And then you look at the 4 and it's either 2 and 2 or 4 and 1. Well, 4 plus 1 is 5. So if this type of thing is taking you more than 10 seconds, you need to go to Khan Academy and go to their factoring thing and go through, 5 hours of factoring practice. And again, it's completely fixable at this stage, but you need to fix your algebra and your trig stuff now. Because in Calc 3, when you jump into 3 dimensions, if your trig sucks, your life is going to suck. Because it's that dramatic. It's like, and you don't want to go through a 5-credit Calc 2, get a C-, get into Calc 3, and then all of a sudden be no hope of passing. Because then really what you need to do is drop the Calc 3 and probably go back to Calc 2, because Calc 2 reinforces the algebra and the trig more than any of the calc classes do. So then you're just really hosed if you decide to try to go on without really having your Calc 2 down. So this is the class where you can fill in the trig holes and the algebra holes and be confident that you can do Calc 3, you can do differential equations, and you can do physics 2. So you just have to think carefully and make a good decision. If your decision is to withdraw, because it's way better to have a W than an F or a D on a transcript when you're trying to get into an engineering school. Those are bad things to have in your transcript, an F or a D. W you can always explain. My mom got so sick. I just had to drop out and help her, nurse her back. The cancer was horrible. There's all sorts of things that you can explain a W away, but you can't explain an F away. Like that you didn't take the time to get online and hit drop. That's inexplicable. Right? You can't explain that. So you want to think about that. And then the other thing is, if you do choose to withdraw so that you can strengthen and retake, you have paid for this class. Come to the end. Even if you have to retake, the best thing you can do if you think you're going to retake, to just drop and leave, you're not doing yourself any favors. You've paid for it, and it's totally fine if you withdraw and just stay to the very last day of the semester, right? You've paid for it. The upstairs, of course, they think differently, and they say as soon as you've dropped, you cannot come back through the door. But we're not telling them. So, and I've seen this many times with students that are dedicated, they want to get their degree, they don't do well, they have to withdraw, they stay to the end of the semester, and they ace it the next semester because they're caught up. It's the second time through one of these classes is much better than the first time, if you're suffering, if you're having a hard time. But if you're having a hard time, it means you have algebra holes and trig holes you've got to really work at filling in. And basic Calc 1 derivatives maybe. So, anyway, and ask me if you have questions on what your option, what you feel like might be a good option or not a good option, and we can talk about it. But, I want you to be successful in your engineering choice. The other thing to think about these days is that the job market is very hard. And so sometimes we've been in those economic situations where GPA doesn't matter. There's many periods of time where GPA doesn't matter, and if you've got the engineering degree, you're good to go. We are not in one of those times right now. Right now, they are looking at transcripts. They are selecting. The unemployment rate for Gen Z right now in the sciences is atrocious. It's really bad right now. And so that's another thing to keep in mind is that, it's not a matter of just scraping through and, oh, I got my mechanical engineering degree. I know multiple Gen Zers that got their engineering degree and are unemployed right now, going to Colorado School of Mines. Right now is not the best time to, C's get degrees. Get that out of your mind, because that is not the economy that we're in right now. And it's going to be at least 5, because there's a glut of folks that are moving into the sciences right now. There are more computer science majors right now than ever. And the computer science demand right now is tanking with AI type stuff. So think about those things too and make good decisions. And if you want to do the engineering route, that's great. But be thoughtful about it, because it's not like it was 10 years ago where you walked out the door with an engineering degree, you were making $80,000 in your first year. It's just not that way right now. So keep those things in mind. And if you have questions and you want some tips, I can give you some ideas.
Wait, real quick before you
Yeah.
change the page.
Yeah.
So, since the explicit is n squared, you want to keep it like the what's it called? The recurrence within squares and square roots, because it's also a sub n plus 2n plus 1.
For this one?
Nope, for
this one?
Yeah.
Say that again. It's also.
a sub n
Yep.
plus 2n
Yep.
plus 1.
Yeah, you could if you FOIL this out, you would get to something different also. Yes.
Yeah.
Yeah, you can, there are often multiple ways.
Okay.
Often multiple ways, especially with recurrence. Sometimes with recurrence, you can go back you can do all sorts of things with recurrence. As long as you have a formula that's giving you the right answer, it's fine.
Okay.
Yeah. So it's easy to grade. If it gives you the right answer, it's true. Okay, so let's look at some of this sequence stuff. So this should be mostly reviewed. The only difference is that in Calc 1 you had an x and now we have an n. So we are thinking of dots instead of continuous curves. And so we've got this function here, and the instructions say write out the first handful of terms. If the sequence appears to converge, make a conjecture about its limit. If the sequence diverges, explain why. So let's take a look at, it's always helpful, one of the other things on the test, graphing. You have to be able to graph the basics, e to the x, e to the negative x, those things. You've got to be able to graph those things. Make sure, if your graphing is bad, start practicing. Put it on note cards. Note cards are amazing. So plugging in a 1, 10 minus 1 is 9. Plugging in a 2, 100 minus 1 is 99. And we can see pretty clearly that this is a sequence that is going to do what? Converge or diverge?
Diverge.
Diverge, right? What's the explanation? The terms are growing without bound. Or the terms are not approaching a single number. Right? For a limit to exist, the terms have to approach a single number. So you could describe the divergence by saying the terms aren't approaching a single number, or you could say they're growing without bound. Growing without bound gives you a better visual sense for what's happening to the terms in the sequence. They're getting bigger and bigger and bigger and bigger. They're growing without bound. So either one of those things. So the terms are growing without bound. Next one. Here we have a 10 to the negative n. Now I mentioned this before the exam. I'll mention it again. For 99% of human beings, it is easier to evaluate a limit if you have no negative exponents. There were several of you that on the exam decided that you would just try to evaluate the limit with the negative exponent. And I don't think I think there was one person that did that correctly. If there's negative exponents, get rid of the negative exponent. It's much easier to visualize what's happening. Unless you are very good at visualizing exponential decay, which you can be, that's fine. Like if you look at this 10 to the negative n and you just see that it's a ski slope going down to the lodge, that's fine. You can do that. But if you don't see that crystal clear, get rid of the negative exponents. It's easier to think in your mind about positive exponents. As this n is getting larger, the denominator is getting bigger, so the fractions are getting smaller. Like we can often boil these concepts down to really simple ideas. Denominator is getting big, that means the fraction's getting small. This is much more abstract. You have to visualize the graph, it's a ski slope, and that's fine if you can do that. But most of the time on the exams, when I see people not go here, more often than not, that's where the mistakes are. So when we look at this and we take the limit here, the limit of a sub n as n goes to infinity, we are going to end up with 1 minus 0, which is 1. So this part here, that part right there, is going to 0. It's a little easier to see it if you get rid of your negative exponents. So the overall limit is 1, and if we look at the graph here, sometimes when you go to Desmos or some of these graphing utilities, it doesn't take very many terms, and the dots are all of a sudden look like they actually are equal to 1, when we know that these are not equal to 1. So if you look at the table feature in Desmos over here, you can set up a table feature pretty easily, and you can see that we're not actually equal to 1, but we're approaching 1. The graph looks like we're equal to 1. Okay, let's take a look at a couple of recurrence ones. So this is a recurrence one, and I sort of I just kept doing it in Desmos again and again. Bless you. So the first term, they have to tell us what a sub 1 is. We need to know where we're starting. We're starting at 1. All right, then we plug 1 in. 10 divided by 1 is 10. Then we plug in the 10. 10 divided by 10 is 1. Then we plug in the 1. 10 divided by 1 is 10. Then we plug in the, oh! And what do we see is happening? Are we approaching a single number?
No.
No. We're in an infinite loop, right? We're just bouncing back and forth between, we started at 1, we jumped to 10, we went back to 1. So we're just doing this type of thing. So is that going to converge or diverge? Is that sequence approaching a single number? Nah. Right, it's oscillating between two numbers. So this is diverging. So this diverges. And you can say by oscillation. Or you could say because the terms are not approaching a single number. Something like that. Doesn't matter. Several ways to describe it. Here's another recursive one. So this one starts at 2. This one starts with a 0 as the first index. So 2. Right there, a sub 0 is 2. And then we plug in the 2. 2 divided by 2 is 1. 1 plus 1 is 2. So we're back to 2 for a sub 1. Plug in the 2. 2 divided by 2 is 1. Add 1. We're back to 2. So this sequence is a constant sequence. And does that converge or diverge? It has to do one or the other. A sequence either converges or diverges.
Convergence.
has to converge because it's getting arbitrarily close to 2. It's always within a skosh of 2. Right? It's actually equal to 2, so it's within a skosh of 2. So the limit of this one, so the limit of a sub n is 2. So it converges to 2. The limit is 2. Say lots of things. Okay, now when you have a recursive sequence that converges, you can find what it converges to with a little trick. Maybe I shouldn't call it a trick. If you take the limit of both sides of this right here, so the limit as n goes to infinity of the left side, so a sub n plus 1, and you take the limit as n goes to infinity of the right side, 1 plus a sub n over 2, and we assume, so here this only works if you are darn sure, because you've looked at empirical data, and you're pretty darn sure that it does converge. If you're darn sure that it converges, so you assume that the limit is L, then you can do this to actually find L. So if somebody says, here's a recursive sequence that converges, and their reasoning might be that they looked at 5,000 pages of data, this technique will find the limit of a recursive sequence that converges. But you can't, it does not work if the sequence diverges. It will give you a bogus answer. So if you're pretty darn sure the sequence converges, you could do this. This you can treat as a sequence just like the a sub n sequence. N in this case starts at 0. So if you were to just look at this sequence here, a sub n and n starts at 0, you should be envisioning a sub 0, a sub 1, a sub 2, a sub 3. This one, it's just another sequence, but it's very closely related to that sequence over there. This one, if n starts at 0, it's starting with a sub 1. So this sequence is a sub 1, a sub 2, a sub 3, a sub 4. This one is a sub 0, a sub 1, a sub 2, a sub 3. If you chop off the beginning of a convergent sequence, does that change its convergence? Like if you chop off the first 1,000 terms, it doesn't matter. If the sequence converges, the tail of it's still going to approach that limit. So these two sequences are identical except that one starts at a sub 0, this one starts at a sub 1. They have the same limit though if you assume that a sub n is converging. If a sub n converges, a sub n plus 1 converges. So then you can do this whole crafty algebra technique. Subtract the L over 2 to the left. We get that, and we get that L is equal to 2, which we kind of already knew based on our data. We saw that it was just sort of repeating the 2. So if you have a recursive sequence that converges, you can use this clever little idea to find the limit if you can't see it from your data. So infinite series. So that's the basics for sequences. We talk about limits of sequences. That's the most important thing for a sequence. The limit of a sequence is the most important thing. So practicing some limits, super important. What is a series? So first off, again, a series is infinite unless they tell us otherwise. Series means sum. So we start with a sequence of terms. So we've got a sequence of terms, and we're going to take that sequence of terms and we're going to add them all together. And we're just adding them all together. So we have a big pile of numbers and we're adding them all up. And we want to know, is that finite or infinite? Just like improper integration. We've got this unbounded tail of a function. Is it finite or is it infinite? Same exact question. So we've got this big bowl of numbers. We're adding them all together. Do we need a bigger bowl, or is it finite? Can we add them all up and get a finite answer? Now, there is a secondary sequence that we need to talk about. The secondary sequence is called the sequence of partial sums. And it is what it says. It's a sequence so infinite sequence, of partial sums. So we're going to bootstrap our way through this. S sub 1 is just the first term. S sub 2 is the sum of the first two terms. So we're going to do this thing where we just keep adding one term and create a whole new sequence called this partial term sequence. And so we create this S sub n sequence. And if we look at the nth term of the S sub n sequence, it's going to be the sum of the first n terms. So that's what the sequence of partial sums is. We just are going to look at this new sequence, and each term is a partial sum. And very important, S sub n is the sum of the first n terms, no matter what the index is. If this starts at 0 instead of 1, the last term would be a sub n minus 1. S sub 5 is the sum of 5 terms. Whether you count them 1, 2, 3, 4, 5, or 0, 1, 2, 3, 4, it's 5 terms. So we want to keep that in mind, that the index and the initial index value doesn't matter. If we had an initial index value of 2, we would count them as 2, 3, 4, 5, 6. S sub 5 means 5 terms, regardless of where the n starts. So, here is our series. This is S sub n right there. That's the sum of the first n terms. And this should look so similar to improper integration. So with improper integration, we had an infinite tail. We chopped off the front part, and we got a finite, right? We got a definite integral. But that definite integral was a function of whatever letter we had, an A, B, or C, depending on what we were doing. And then we took the limit to find the entire area. Same idea here. So we're going to look at the front end like we looked at a definite integral. So we get this. This is going to be a function of n, because there's an n right there. And then we just take the limit of that function of n. If we get a number, the series converges. If we don't get a number, if the limit doesn't exist, then the series diverges. Every sequence, converge or diverge. Every series, converge or diverge. There's only two sides to the coin, one or the other. So, if the sequence of partial sums diverges, the infinite series diverges. If the sequence of partial sums converges, the series converges. And we say this in a lot of ways. You can say the series converges to L, the sum of the series is L, the value of the series is L, the series approaches L. So we use the word approach and equal to kind of interchangeably, even though there are some very slight differences in those two concepts. So let's look at a basic example. Every repeating decimal is an infinite series. These are the most elementary infinite series. You've all dealt with them many times in your life, maybe not realizing you were dealing with an infinite series. So this infinite series, 0.6 plus 0.06 plus, etc., that's an infinite series. You're adding an infinite number of positive numbers together, and we know that this is going to converge. This is going to be equal to 0.6 repeating, or as we know, all repeating decimals can be written as a rational number, a ratio of integers, so that's going to be that. So for the following infinite series, find the first 4 terms of the sequence of partial sums, then make a conjecture about the value. So let's do it so this is kind of our base. We already know it converges. So let's see if we can use that information to our advantage. So let's find the sequence of partial sums. So our sequence of partial sums, S sub n, will be, the first term is 0.6. The next term?
0.66.
0.66, exactly. So we're just going to add one more term, and we end up with a sequence of partial sums that looks like that. And we can see that the limit of S sub n, as n goes to infinity, is equal to 0.6 repeating, which we know is 2/3. So that series converges to 2/3. Now, these two examples, of course, are, we always start with examples that you don't really need calculus to even analyze. You just use algebra there. Similarly here, the sequence of partial sums in this case starts at 4. That's a sub 1. We always assume that we're dealing with a sub 1 unless otherwise stated. When we get to geometric series, we'll see that we often start with 0. But for the most part, we usually just think that we're starting at 1. It's easier to count if you start at 1, at least for me. So there's our sequence of partial sums. And the limit as n goes to infinity of this sequence of partial sums is going to be equal to?
5.
Mm-hmm. Limit of that will be 5. So the one number that this sequence is approaching is 5. If you pick any other number other than 5, you can prove that it's not the limit. But 5 is the limit. These numbers are getting arbitrarily close to 5, infinitely close to 5, indistinguishable from 5. Lots of ways you can think about it. All right, so let's go ahead and take a break now. If you want, you can look at this thing. During the break, if you're bored, take 10. All right, let's take a look at this infinite series. If you think about this infinite series, if you think about the graph of this exponential function, right, this is 1/2 to the k. The denominator is growing exponentially there. So it's going to go to 0 very fast. So if we think about what we did with improper integration, that curve, that's an exponential decay. You can think of it as 1/2 to the k or 2 to the negative k, doesn't matter. It's going to ski slope down to the lodge. That's going to decay really fast, so we would expect it to converge. So infinite series, though, the way we analyze infinite series is that we look at this sequence of partial sums. That is our avenue in. We always look at the sequence of partial sums when we're analyzing a series. Now, most of the time, finding a formula for S sub n is very hard, most of the time. If you have a formula for S sub n, then you just take the limit as n goes to infinity, and it's simple. If you have the formula for S sub n, what we are going to see, and the reason you have this thing that you probably have seen, where do I have it? Well, I know that I have it over here. If you look at the handouts, this thing, all this stuff, and there are the convergence tests. The reason we have this big old thing is because 90% of the time you cannot find S sub n, so you need another way to analyze whether a series is going to be finite or infinite. And that's what all these tests are. So this chapter, if you want, the handouts that apply to this chapter are starting right here, and these 4. These are all for this chapter. 10 and 11. Oops. 10 and 11. And that's what these tests are for. These are for when you don't have S sub n. When you don't have S sub n, how do you analyze the convergence or divergence? Okay, so let's see, we are here. So this happens to be a series that we can find S sub n for. So let's see how easy it is to find the sum of this series when you, well, actually, let's see how easy it is, to find the sum of the series when you know S sub n. So here is our sequence of terms, and then we build the sequence of partial sums. So the sequence of partial sums is going to be 1/2, that's S sub 1, followed by 3/4, followed by 7/8, followed by 15/16. Okay, so there's our sequence of partial sums. Now, we need to figure out S sub n in general so that we can take its limit. Okay, let's see if we can come up with a pattern. Well, notice the index value and notice the denominator. Let's focus on the denominators first. How are we getting to the denominator from our index value?
Just x2.
So it's 2 raised to that index value. This is 2 to the 1, this is 2 to the 2, 2 to the 3, 2 to the 4. Right? 2 to the 4 is 16, 2 to the 3 is 8, 2 to the 2 is 4, 2 to the 1 is 2. So each of the indices corresponds to a power of 2 in that denominator over there. Bless you. Everyone see that? 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. So that is the exponent on 2. Now, this one is really simple to find the numerator because how is the numerator? How do you get the numerator from the denominator? Just subtract 1. Right. So the numerator here is 2 to the n minus 1. So that's about as easy as it gets when you're trying to figure out a formula for S sub n. Again, 90% of the time you cannot discern the pattern. Yeah, and so that makes it complicated. So there is our S sub n. We did discern the pattern here, so we're golden. Now we just need to take the limit of this. So the limit as n goes to infinity of 2 to the n minus 1 over 2 to the n. Well, that's an indeterminate form, infinity over infinity, so we have to do something so that we can analyze it. We have to do something to change the way it looks. And the thing to do is to split the fraction. You can split a fraction like that. So we're going to have 2 to the n over 2 to the n, which is 1. Now this we can analyze. We have a constant, limit of a constant is itself. And then we have a basic fraction where the top is constant at 1 and the denominator is going towards infinity. So the fractions are going to 1 over 2 to the n is going to go to, where's 1 over 2 to the n going to?
0.
0, right? That is going to 0 because the denominator is going to infinity. The fraction has a constant numerator, so the fraction values are going to go to 0. So this limit is 1. So that tells us that the sum of the series is 1. That means that you can say the series converges to 1. You could say that the value of the series is 1. Say either of those things. So we have 1 over 2 to the n. Do we use an n or a k? Kind of depends on the context. 10k started at, did it start at 1 or 0? Or started at 1. So 1 to infinity. So this is equal to 1. So therefore, the series has value 1. The series converges to 1, however you want to say it. So if S sub n converges, the series converges. And another way to think of this is if you looked at the graph. Now this is interesting, I guess. So here is 1 right there. It's going to go down like that. And this series started at 1, and 1 comma 1/2, so let's maybe make that right there. So that's at 1 comma 1/2. Okay, so the series converges to 1. The value of the series is 1. That doesn't necessarily mean that this area is 1. So we would have to go through the improper integral technique that we learned in the last chapter. So this converging tells us for sure the area is finite, but the area might not be exactly 1 depending on how you set up your equation. Could be a little different.
So
Sebastian?
what's the difference between the list of an equals the 1/2 and
That-
the one that we just did?
This is the sequence of terms. This is the sequence of partial sums. So the first terms match, but then the second term down here is the sum of the first 2 terms. So S sub 2, so S sub 2 adds these 2, S sub 3 adds those 3, S sub 4 adds those 4, S sub 5 adds those 5, and that's what these are. So these you're partially adding. You're adding the first 2 terms, the first 3 terms, the first 4 terms, the first 5 terms.
So the first step is just convert an to Sn.
Yes,
Okay.
because so if you were to look at a graph of a sequence, there are 2 things. You can look at the graph of the terms, or you could look at the graph of the sequence of partial sums. Where do I have do I draw a graph up here somewhere? So here, this is the graph of the terms of the sequence. The graph of the sequence of partial sums is going to be different, because the sequence of partial sums, you're adding terms together. So let me ask you this. Do you think this, if I turn this, so this is a sequence of terms, if we then convert it to a series, do you think this series would converge or diverge? Diverge. Because the terms are approaching 1. So that means if you added them all together, if you think about your sequence of partial sums, you're basically adding 1 to itself infinitely many times, which is going to diverge. Everyone following that? So the terms in this sequence approach 1. So if you go out to the tail in the sequence, it's kind of like 1, comma 1, comma 1, comma 1, comma 1, etc. Now if you're starting to add them all together, you're going to get infinity. The only way you can add an infinite number of positive numbers together is if those numbers are getting tiny. So they have to approach 0.
Will they always have this type of relationship?
Yes.
Okay.
Yeah, so anytime we have a sub n, that's just the list of numbers, s sub n is always going to be that ratcheting further and further out in the series. And if a sub n converges to anything other than 0, your infinite series diverges. If your a sub n's converge to 0.1, then it's like you're adding 0.1 to itself an infinite number of times, which diverges. It doesn't matter how small a positive number is. If you add it to itself an infinite number of times, it's going to diverge.
So does that mean that if we have a sequence that is divergent, does that mean then that the series is going to be convergent?
If the sequence diverges, the series is going to diverge.
Okay.
Right, because if the sequence diverges, like let's suppose the sequence diverges to infinity, 1, comma 2, comma 3, comma 4, comma 5, when you add all those together, you're going to get infinity. So if the sequence diverges, the series will diverge.
But what if we had a sequence that was like the oscillating -1, 1, -1?
Okay, great question. So if we have that sequence, if we have this sequence, so did you say 1, -1, that
Yeah.
one? So if we have this sequence right here,
Zero.
so we have that. So let's look at our sequence of partial sums. So our sequence of partial sums, so here's a sub n, the sequence of terms. The sequence of partial sums will be 1, and then 0, and then 1. Does that sequence converge? No. Right? So the limit of S sub n here, all we can say is that it does not exist. Often we would say if it does go to infinity, we would write equals infinity. We only write d and e if we can't be a little more descriptive. Like if the limit is infinity, that does not exist, but we usually write infinity because that describes how it doesn't exist. So this tells us then that this series would diverge. So that series, this series, the series that does what you were saying, so the series where if we can create this series, let's see, so this is going to be, I'm going to make that n plus 1, and I'm going to start at 1, go to infinity. This book uses a k for this context, so let's put a k there and a k there. So this would be that series, right? This is going to be, when you plug in the 1, you get a positive. When you plug in a 2, you get the negative. So this is that series. And this series is going to, it's going to diverge. We can't say infinity, so this sum will not exist. That sum does not exist. Because the sequence of partial sums oscillates. The sequence of partial sums does not have a limit. So the only way a series can converge, same as with the improper integrals, is if the terms go to 0 very fast. So the terms have to go to 0 very fast, which is what we just witnessed in that one example right here. So when you look at the a sub n's here, the terms are going to 0, and they're going to 0 very fast. When the denominator is an exponential expression with a number bigger than 1 right here, so a 2 or a 3 to the k, 4 to the k, 5 to the k, that grows so fast that the fractions go to 0 so fast. So that's kind of a very similar type of thing that we've seen with the improper integrals. So if the sequence of terms goes to 0 really fast, then the sum is going to be finite. But that sum doesn't necessarily mean that this area is 1. We have to do the improper integral technique that we did in the last chapter. It might match, but it could be a little bit off.
Does it mean anything?
The 1?
Yeah.
Yes. It means that if you add all those together, you get 1.
Okay.
That's what it means. So it means that if you take and put a plus instead of all those commas, that will add up to 1, which is remarkable. Right? 1/2 plus 1/4 plus 1/8 plus 1, it's equal to 1. That is the sum of that infinite series.
But it has to go to infinity for it to equal 1, because like s sub 1 is 1/2.
What was your comment?
It has to go to infinity to equal 1 though.
What do you mean it has to go to it? Oh, yes, the
Yeah.
number of terms.
Yeah.
Yes, if you stop at 100 million terms, you're not quite to 1 yet. So that's that weird chasing the dragon's tail thing where you're never quite at 1, because as soon as you stop, you're not at 1, but you have to keep on going, and it will be 1. So yeah, it's one of those paradoxy type things. Okay, so let's look at some other sequences. Here is our theorem that gets at something I alluded to earlier. So here we have a function, and we are creating a sequence from that function. The black curve is the function x divided by x plus 1. That's that black curve right there. The red dots are the sequence. So the sequence is a subset of the graph of f. So the sequence is a subset of f, right? It's not all of f because the sequence is just dots. There's holes, right? There's gaps. But, and remember that the sequence, the index values increase by 1, so there's a very rigid stepping through the function. N is 1, and then 2, and then 3, and then 4. You're not like all wishy-washy with, indices that aren't 1 unit between them. All the indices are 1 unit apart. So that forces the dots to be in this pattern, and that function converging to L means the subset of dots has to converge to L also. Okay, so that is our theorem. Our theorem says that if the function f of x converges to L, then the limit of the sequence, come on, is also L. If the function had a limit of plus infinity or minus infinity, the sequence would also. So this is the best case scenario. If you end up with a function that you can take the limit of easily, well, then you can just take the limit of the function, and that's going to match the limit of the sequence. So both of those converge to 1. The converse of this is false. So let's understand what converse means. So this says if the limit of the continuous function is L, then the limit of the subset is also L. The converse would be if the limit of the subset is L, does that mean that the function also converges to L? And the answer is no. So let's look at this example right here. Let's make that a little bit bigger. So the function here, let me write this out more explicitly. I was just playing with this earlier. So if we look at this function, let's turn it into the continuous function, cosine of 2 pi x. So that's the function. That's the blue curve right there. Does that function have a limit? That blue curve? Does that blue curve approach a single number?
No.
No way. It's oscillating. That does not approach a single number. The limit of f sub x as x goes to infinity does not exist. As x goes to infinity. Because it's just oscillating. It's wobbling around. Does not approach a single number. But if we look at this subset, cosine 2 pi n, that does have a limit as n goes to infinity. Right? So if we do n equals 1, cosine of 2 pi, 1. If we plug in n equals 2, then we have cosine of 4 pi. Cosine of 4 pi, we've gone around the unit circle twice. 1. Cosine is the x-coordinate. So this is really just the sequence 1, 1, 1, 1, 1, 1, 1, 1. It's a constant sequence that converges to itself. So it converges to 1. So this converse is false because we found a subset that has a limit, but the parent function, the superset, does not have a limit. So if the superset, the continuous function, converges, then the subset has to converge. But just because you found a convergent subset doesn't mean that the superset or the parent function converges. So it's only one directional. One direction only. All right, let's take a look at some limit laws. These are identical to what you did in Calc 1 for functions f and g. So if you have the limit, if you have a pair of functions and their individual limits exist, then if you add the functions or subtract the functions, then the limit still exists. So the limit of a sum is still a sum of limits. The limit of a difference is still a difference of limits. Same as it was for Calc 1 for limits of functions. So this one's same also. If you have a constant times a function that converges, you can factor the constant out. Same thing here. If you have two functions that converge, then their product converges. If you have two sequences that converge, then their product also converges. And similarly for the division. If you have two sequences that converge, then the quotient converges as long as the denominator does not converge to 0. So identical with functions in Calc 1. And then here's just a statement. When you're thinking about the sequence, you can imagine chopping off as many of the leading terms as imaginable as you need. It does not matter. It's the tail of the sequence where the terms have very large indices. It's those terms that dictate the convergence of the series, of the sequence. So the beginning 5 million terms could be doing something crazy up and down all over the place, but if the tail steadies down to 0, then the sequence converges. Right? So if you have two sequences and they have leading terms that are different, but their tails are the same, then they converge to the same number. Right? So the convergence of a sequence all depends on the tail. You can chop off the first finite number of terms, and you still have the same limit.
What do you mean by tail?
Tail is what happens to the right of n. Tail is when the index values are huge. Like our sequences have an infinite number of terms, and it's all relative. Like if you have a sequence and it does this for the first 100 terms, but then it does this for all terms greater than 100, then the tail is n greater than 100. You know, so the leading terms versus the tail is just the leading terms are the front of the sequence, and the tail is the end of the sequence. And regardless of what happens in the beginning, the tail is what dictates whether the limit exists or does not. So you can have all sorts of craziness in the first 1 million terms, but then if it steadies down and is converging at the end, then it converges. So the leading terms are meaningless when you're talking about the convergence or divergence of a sequence. The leading terms are meaningless. So, and that is why the initial index of a sequence is often not even, a lot of times you don't even know what it is, you don't even care what it is. Because you really just care about what happens when n is really big. And so sometimes, quite frequently, they don't even tell us whether it starts at 0 or 1 or 5, because it doesn't matter. The tail is what matters when you get farther out in the sequence. That is what matters. So let's take a look at some of these examples. So review from Calc 1. So same as Calc 1 when you took limits of functions. So we're taking the limit of these functions as n goes to infinity. And what we notice right away with this one, as n goes to infinity, if we just analyze it as it's presented to us, we get the indeterminate form infinity over infinity, which a lot of times I'll write it like this. So that means something. In Calc 1, you could use L'Hopital's rule. If you have infinity over infinity or 0 over 0, you can take the derivative of the numerator, derivative of the denominator, and then reevaluate the limits. That would be a pain in the neck here, because we would have to take how many derivatives to get down to a limit that we could evaluate. Right? We'd have to differentiate. If we differentiate once, then we have a power of 11. Twice, we have a power of 10, all the way down. We have to differentiate like 10 times. Pain in the neck. That's not what we want to do. So you learned other techniques in Calc 1. You divide by the highest power of n. That was a common technique. So we look through here, and as long as you divide every single term by the highest power of n, you still have equality. It's like multiplying by 1. Dividing top by n to the 12, dividing bottom by n to the 12, that's the same thing as multiplying by 1. So once again, we use that technique, multiplying by 1. It's our favorite technique. And so what we did was divide everything by n to the 12, which again is equivalent to multiplying by 1. So you don't change the value, you just change the look. So if you divide everything by n to the 12, we get that. And now we reevaluate the limit, and we're golden. Now we can evaluate it. This term right here, 4 over n to the 12, where does 4 over n to the 12 go?
0.
0, right? That's one of our basic limits. Constant numerator, exploding denominator, terms are going to 0. So what's the overall limit?
1/3.
1/3. So that is the limit of that sequence, 1/3. All right, you all try this one. Try to find the limit of this second one. See if you can do that. I'll write it out while you try to do it. once again, you have an indeterminate form, infinity over infinity, so you have to do something. You have to change the look of it. You have to massage it in some way, aka multiply by 1 in some weird way that's going to allow it to be evaluated. There are two natural choices to divide by. N to the 3 or n to the 5. Those are the two things that sort of jump out at us as viable things to divide by. And it kind of depends on what you're most comfortable with. Let's take a look at dividing by n to the 5th. Let's just blindly say, divide by the highest power of n. Totally legitimate. That is fine. That is, at its core, multiplying by 1. So if we divide everything by n to the 5th, we will end up with so that's what we end up with. And where do all of these individual little fractions go?
0.
Yeah, they're all going to 0 because they all fall into that basic limit example where the denominator is exploding and the numerator is a constant, so the fractions are going to 0. All right. We have division by 0 here. Right? The denominator is going to 0. First question, is the denominator positive? Is the denominator negative, or does it oscillate between pluses and minuses? It's always positive. So the denominator is going to 0 from the right. It's going to 0 through positive values. So 1, 1/10, 100th, 1,000th, 1/10,000th, 1,000,000th. Right? It's going through positive values down to 0. The numerator is going to plus 1. So are the fractions positive, negative, or some mixture? The fractions are always positive because the top's always positive, 1. The bottom's always positive, going to 0. So 1 divided by 0 in this case is going to be positive infinity because everything is positive. The denominator is going to 0, but the top is constant. So then you have that situation we talked about before. 1 divided by 1 is 1. 1 divided by 1/10 is 10. 1 divided by 100th is 100. 1 divided by 1,000th is 1,000. So this is going to go to infinity. Question?
I forgot the question.
You forgot the question?
Yeah.
Oh, maybe I answered it.
No.
Okay. If it comes back,
And then if you divide by n to the 3rd, you get the same thing.
yes. And if you divide by n to the 3rd, let's do that one.
You get n squared over 10, basically.
Correct, exactly. So you're still going to have the same answer, but if you divide everything by n to the 3rd, you have this.
The last two terms go to 0.
These two guys go to 0. These are our basic limit. So that's 0, that's a 0. Now we have that basic limit where the top is going to infinity and the denominator is constant. So that means the fraction values are growing without bound. Right? These both go to 0, so they're insignificant. Top is going to infinity.
Yeah, I found it. The first one, the entire thing will be turned into 1 over 0. Wouldn't be, it does not exist.
So we're talking about a limit, not a value. So if somebody said, what is the value of 1 divided by 0, you would say that does not exist. Right? That's undefined. But that's not what we're asking. We're finding the limit where the numerator is going to 1 and the denominator is going to 0. So limit is different than a value. So we can't divide by 0, that does not exist. But you can evaluate a limit. And we say that the limit is infinity, which means the fractions are getting bigger and bigger without a bound. That's what this means. So if the denominator is going to 0, but you're coming to 0 from positive numbers, and the numerator is going to 1, and it's always positive, the fractions are always positive, but they're going to be getting bigger and bigger and bigger. So as you divide by a number, if this is constant up here and you're dividing by a number that's going to 0, the fraction values will go to infinity. And that way is much harder to analyze than this way. This way is a little simpler. So a lot of times, to simplify it, instead of dividing by the highest power of n, the rule might be for you, divide by the highest power of n in the denominator. That often is an easier way to analyze. Both will work, but down here it's a little bit easier because you can see these go to 0, this is a constant, and the top's blowing up, so this is that limit is going to be infinity. So it's your call, but dividing by the highest power of n in the denominator might be the easier way to make that final conclusion. All right, so let's take a look at this one. So the limit here of inverse tangent of n as n goes to infinity, what you should be visualizing in your mind is this function that we've analyzed to death, the inverse tangent function. So here is a picture of the inverse tangent function. We know that the inverse tangent function has asymptotes there and there. This one is at pi over 2. This one is at minus pi over 2. So now when we visualize this sequence, it didn't tell us where they start. So we can imagine it starting at 0 or 1. Does not matter where we decide for it to start. Let's just suppose we chose 0. So now we have our sequence is embedded within that function. So that sequence is embedded within that function. And we know that the limit of the function, what is the limit of the continuous function as x goes to infinity? Yeah, pi over 2. Right? That's what that means. It's got a horizontal asymptote. So its limit at infinity, if you will, is pi over 2. So therefore, we've got this continuous function that has a limit. Therefore, the embedded sequence must have the exact same limit. That sequence must also go to pi over 2. Must have a limit of pi over 2.
And that's because we were given positive infinity, that it's positive pi over 2.
Correct. Yes. So if the limit said as n goes to negative infinity, we would get negative pi over 2. Correct. Mm-hmm.
Sorry, I had a question.
Yeah, sure.
So, trying to understand the difference between n and x. So n is basically like those integers.
Yep, positive integers. I mean, n can be any integer technically, but usually in the context of sequences, we imagine it being positive integers or non-negative integers if it starts at 0. So and kind of in math, we sort of associate m, n as usually coming from integers. I and j also usually integers. I, j, and k usually integers. Usually a, b, c we think of as real numbers usually. X and y we always think of as real numbers. So we kind of have those letters that we have these designated roles for. So when we see a function that's got an n in it, we should be thinking salt and pepper. We should be thinking dots. You know, we think individual dots. Whereas when we see the x, you're imagining not picking your pencil off the paper kind of thing. Right? You're going to get a continuous function unless there's an asymptote or something. But, yeah, so that's kind of our convention. X continuum, n discrete. So discrete means that you're picking off individual points. So you have, for example, the positive integers. Here is a technique that you all loved or maybe loathed in Calc 1, which is going to come back to you. So hopefully it's not something that's going to be too difficult, because it is something you did in Calc 1. And the root of what we're going to talk about comes, you should have first been exposed to it in college algebra. In college algebra, and maybe even intermediate algebra, you were dealing with compound interest, and you would deal with things, you know, like I forget the interest formula. It doesn't matter what the interest formula is, but let's suppose you had something like this. So let's suppose you have that. And in college algebra, you would talk about limits at infinity, which is hidden, that's hidden limits, right? You're taking limits. I guess in college algebra you didn't call it a limit at infinity. What did you call it? You called it a horizontal asymptote, right? You wanted to find the horizontal asymptote, and so in calculus you would have called it find the limit at infinity. But in college algebra, you start with that compound interest rate, and as the number of compounding periods goes to infinity, you ended up with what letter in your formula for compound interest that was continually compounded? You ended up with a famous letter inside that integral, inside that value, P principal times E to the RT, PERT. You ended up with that. And so in college algebra, they just sort of wave their hands and they say, oh, if you look at the graph, this thing is approaching 2.71. And then in Calc 1, you use this technique. So let's talk about this limit here for a moment, because this is super fascinating. If you take a number less than 1 and you let n go to infinity, what does that limit equal? So you take a number less than 1 and you multiply it by itself forever. What's that limit going to be?
0.
0. Half times a half is a fourth. The fourth times a half is an eighth. An eighth times a half is a 16th. The 16th times a half is a 32nd. Right? 0.9 times 0.9 is 0.81. 0.81 times 0.9 is 0.7 something. Any number less than 1, if you multiply it by itself repeatedly, you will get 0 as the limit. All right? Any number greater than 1, you multiply it by itself repeatedly, you get infinity as its limit. Right? You imagine 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, etc. Any positive number that's bigger than 1, if you multiply it by itself repeatedly, goes to infinity. All right? When you look at this, the base, 1 plus 1 over n, is always positive, and it's always bigger than 1. So most college algebra students would say, the limit's probably infinity, although they might not use the word limit. Right? Because this is always bigger than 1. But what you were shown graphically in college algebra, and what you proved mathematically in Calc 1, is that this limit is
1.
Nope. E. And that's where E comes from. E is the limit of this bizarre looking thing. Let's do this one first, just because that's our basic one. So if we write this as a function, and I'm writing it as a function, you don't have to. When I was in school, they really emphasized some of these subtle details. Like if you're going to take a derivative of a function, the function has to be continuous to take the derivative. If you have the n in the function is not continuous, it's discrete. These days, we're a little bit more lax on that, and you could just leave the n and take the derivative with an n, and it doesn't matter. I, out of habit, will always, if I'm about to take a derivative, I'm putting an x in there. So what you learned in Calc 1 is this process, the log limit process. So now we take the log of both sides. And when we take the log of the right-hand side, we pull that exponent down as a coefficient. Pop it down in front. Okay. And now you are going to take the limit of both sides. So we're going to take the limit of both sides as x goes to infinity. The limit of both sides as x goes to infinity. On the left-hand side, that limit symbol can be moved inside the log function. You learned in Calc 1 that if you have a continuous function, limits can move inside a continuous function. So if you have a continuous function, that limit's superpower is that it can move right inside and take the limit of the argument of this continuous function. Natural log's a continuous function. The limit can push to the inside. On the right-hand side is the interesting side. We are going to, first let's look up here. When x goes to infinity, okay, x is going to infinity. What happens to this whole thing as x goes to infinity? Well, we go inside, 1 over infinity is 0, natural log of 1 is 0. So this is infinity times 0. That's an indeterminate form. And what we do is rewrite that indeterminate form so that we can use L'Hopital's rule. Division by 1 over x is the same as multiplication by x. Right? These two are equivalent. Division by 1 over x, that means multiply by the reciprocal, you multiply by x over 1, and you get what's up here. These are equivalent. Now, this is in L'Hopital's form. Now we have the indeterminate form infinity over infinity. Oh, no. Which over which? 0 over 0. Other indeterminate form. Denominator, as x goes to infinity, is 0. Numerator, as x goes to infinity, is ln1. ln1 is 0. So we have 0 divided by 0. So now we can invoke L'Hopital's rule. L'Hopital's rule says, take the derivative of the top, take the derivative of the bottom. So separate, not a quotient rule, separate derivatives. And the concept is that if you have a quotient of two functions, that should approach the same number as the quotient of the best approximations. All right, if we have f over g, and then we replace f and g with its best approximation, aka the derivative, that quotient should approach the same thing. The quotient of functions should approach the same thing as the quotient of tangent lines. Right? It wouldn't be a great approximation if it didn't give us something close. So in the denominator, that's easier to take the derivative. That's x to the negative 1. So it's negative 1, x to the negative 2. So negative 1 over x squared. In the numerator, the derivative of a log is 1 over the inside. 1 over the inside multiplied by the derivative of the inside. The derivative of the inside, derivative of 1 is 0. Oh, another derivative of 1 over x. So we get a negative 1 over x squared there. That's L'Hopital's rule. So normally I would put these things maybe over the equal sign. So because we're using L'Hopital's rule, put that there just so we sort of know what's happening. Those two guys cancel, right? That fraction and that fraction cancel. Now we reevaluate the limit. So now the only thing left is this piece right here. What's that limit? 1. Good. So on the left-hand side, we have natural log of limit of y as x goes to infinity. And remember, y is what we started with. We're calling that thing y. So if we switch to x's because we knew we were taking derivatives. So we're trying to find the limit of y. So what's the last step here? Yeah, we're going to exponentiate both sides, e to the 1, which is just e. So that's y. That's the calculus way to show that this limit is e. So that is our basic procedure for the log limit process. We need to get to a place where we can use L'Hopital's rule. And that's going to happen in general over here. So in general, we've got that. We're going to use the log limit technique. So we first invoke a function. We say, hey, this sequence is a subset. And you don't have to use the x's if you don't want to, but I will out of habit. This sequence is a subset of this continuous function. So if we find the limit of this continuous function, it's going to be the same as the limit of that sequence. Well, to find the limit of this continuous function, we're going to go ahead and use L'Hopital's, this log limit technique, and eventually use L'Hopital's rule. So the first step is to take the natural log of both sides. And then on the right, we're going to have to do some manipulation. I'll usually combine these two steps right here. I'm going to take the limit of both sides as x goes to infinity. So on the left, I'm going to push that limit inside the log right away. Log is a continuous function. Limit can pass through it. Permeable. And then on the right-hand side, I know that we need to target L'Hopital's rule. So we're going to shove that x into the denominator so that we get an indeterminate form of 0 over 0. So numerator goes to 0, denominator goes to 0, so we can use L'Hopital's rule. So on the left, we have natural log of limit of y. And on the right, we can now use the L'Hopital rule. So L'Hopital says f over g, now form f prime over g prime. Form the quotient of derivatives. Denominator is easier, negative 1 over x squared, again. It's always going to be that way if you have just an x down there, 1 over x. In the numerator, derivative of a log, 1 over the inside, first step. 1 over the inside. That's the reciprocal. 1 over the inside is the reciprocal of the inside. Now we have to differentiate the inside. Well, the inside's a quotient. How do we differentiate a quotient? We use the quotient rule. So we know we're going to have this big old gnarly looking thing here. Quotient rule. Quotient rule. Low, d high. So x plus 5 is the low. D high is 1. Low d high minus high d low. High is x. The derivative of the bottom is 1. So there's low d high minus high d low. All divided by low squared, so x plus 5 quantity squared. So there's our quotient rule. All right, let's leave this negative 1 over x squared for a minute. We're going to leave this x plus 5 over x for a minute. Let's just focus on that quotient rule piece. X plus 5 times 1 is x plus 5. X times 1 is x. So we have x plus 5 minus x, which reduces to just 5. And then we have x plus 5 quantity squared. Okay. So let's see what cancels. One of the x plus 5's cancels. So here's what we're left with. So 1 over x. So I'm canceling one of the x plus 5's. And then there we have a 5 over x plus 5. And then we have a flip. We're dividing by a fraction, so we multiply by the reciprocal, so I'm going to make that negative x squared over 1. I'll write it like that just so I can keep that minus sign kind of tucked into the numerator. Well, one of those x's cancels. So now we're going to have limit in the numerator, we're going to have negative 5x. In the denominator, we have just x plus 5. And what is that limit? There are 3 ways to do it.
It's just -5.
Negative 5. The algebra technique, if you have polynomials of the same degree, you just take the quotient of leading coefficients. That's the algebra technique. Calc 1 technique, indeterminate form. L'Hopital's rule. Derivative tops -5, derivative bottoms 1. Or another Calc 1 technique, divide everything by x and reevaluate the limit. So there's 3 ways that you could do it. Divide everything by x, and you'll have -5, 1, and 5 over x. 5 over x goes to 0. So this limit will be -5 with one of those 3 techniques. Doesn't matter which one you choose. Your choice. The easiest is the algebra technique. Polynomials of equal power, grab the coefficients. It's the easiest one. And then our final step is to exponentiate both sides. So if we exponentiate both sides, the limit as x goes to infinity will be e to the fifth. E to the fifth. E to the negative fifth. So that whole thing converges to e to the -5. So, yeah, question?
This might not work, but because the denominator adds 5, could you just take e and flip the negative and put it as its exponent?
Are we looking right down here?
No, with the original n over n plus 5.
This here? Could we flip this?
Just take the 5, make it negative, and put it as an exponent.
Here, okay, all right, you asked for this.
Oh no!
So, in general, so you see this, we can generalize this. That can be generalized to 1 plus a over n to the bn, and that generalization is going to turn into e to the ab. You can prove this by using the log limit technique. So there is our general form of an exponential, whatever you want to call it. You know, the horizontal asymptote for this function is going to be this e to the ab. Now, what you said, let's see, n over n plus 5 raised to the n. That's what it was, right? Okay, n over n plus 5. So here's what you could do that's sort of similar to what you were just talking about. You can't split this fraction, right? Because the denominator, like if we look at our basic form, it's 1 plus something. Well, we can't force that to be true here quite yet because that denominator has 2 terms in it. So we can't split this fraction or anything. When the denominator is 2 terms, we can't split if the numerator is only 1 term. But we can do what you just said. We can flip this. If we flip that, what happens to the exponent?
It goes negative.
Right? It goes negative. Now we can split this fraction. And we have this. And what is this limit? Well, if we use our general exponential limit, if this is a plus, that's an a, that's a b, all you do is form the quotient, product, a times b. A is 5, right? A is 5. A is 5. B is -1. So this is going to be e to to the negative 5. So that's the shortcut you kind of are getting at. A little bit of a roundabout way, but that's how you could get to that shortcut. That said, on the test, you have to be able to do log limit process when it's asked for. But could you tell me what the limit of this is right away? E to the what? Close. Let's put it in the right form first.
Oh, be the negative 4.
So the right form, I guess we don't need that. We want a plus right there. And that's just 1n. So now there's that a that I mentioned above, and there's that b. So that tells us that this limit is e to the negative 4. So you can use that for sure as a check on the test, but you need to make sure that you can do the log limit process here. So if we're going to do the log limit process for this one, we're going to let y equal 1 minus 4 over x to the x. We'll take the natural log. So we'll get that. Then we take the limit of both sides. And on the left-hand side, we're going to shove the limit to the inside. And on the right-hand side, we're going to force this to be in L'Hopital form. Multiplication by x is the same as division by 1 over x. Now we're in L'Hopital land. That's 0 over 0. So we're going to take the quotient of derivatives. The derivative of the bottom, again, we're seeing this pattern, 1 divided by x squared, negative. Up top, the derivative of a log is 1 over the inside multiplied by the derivative of the inside. The derivative of the inside, derivative of 1 is 0. The derivative over here, we have negative 4 divided by x. So that's really a 4 times x to the negative 1. Right there. So we're going to end up with that same derivative. So we're going to have minus, and then there's going to be another minus, so it's going to turn into a positive, and it's going to be 4 divided by x squared. 4x to the negative 1, you bring the negative 1 down, subtract 1 from the exponent. So if we write this out, we're going to have, as we do some cancellation here, this first piece, there's no cancellation right there. That just comes down. But then when we flip this, the x squareds cancel, and we get a negative 4 in the numerator. So this x squared flips, the x squareds cancel, the minus can go into the top, and we get that. And what is that limit as x goes to infinity? Negative 4. And then we exponentiate both sides. So the limit of y is e to the negative 4. Which, same things we'll get here. So, moral of the story, if you take what you learned in college algebra, which was that, without much justification, make sure you can do that just as a check, but you have to be able to do the log limit process. All right, any questions on any of the steps or that log limit process? Yeah?
Can you go over the red 0 one?
This one?
Yeah.
So the derivative of the denominator is that. Do you agree with that?
Yeah.
And then the derivative of the numerator is 1 divided by the inside of the log multiplied by the derivative of the inside of the log, and the derivative of 1 is 0, so that's gone, so we have to differentiate that piece. And I'm thinking of that as negative 4x to the negative 1, so when you differentiate it, you get positive 4x to the minus 2, which is 4 over x squared.
Okay.
Make sense?
Yeah.
All right. All right, this is what? Start of week 9. So I'll see you on Thursday for the last day of week 9. Holy smokes. And if you have any questions, I'll stick around as long as you need. Stay and ask if you have any questions.